Some of the most natural subgroups of the symmetric group are the ones where you permute the first alpha 1 letters amongst themselves and then the next alpha 2 letters amongst themselves, etc. These are called parabolic subgroups of the symmetric group. So let's let alpha with our components be a composition of n, and we'll define S, capital S alpha, which is going to be isomorphic to S alpha 1 cross S alpha 2, etc., up to S alpha R, to be the subgroup of Sn permuting the first alpha 1 letters and then the next alpha 2 letters etc. And the last alpha R letters, I guess, are going to be n minus alpha R plus 1 through n. This is also called, and probably more often, W sub j, if we think of J as a generator subset, in particular as the generator subset. So all of the generators except for, so we can permute everything here, so except for the alpha 1 generator. And then we can permute everything here, but we're not going to permute those two letters, so, and not the alpha 1 plus alpha 2 generator, etc. And then I guess the last generator we're going to exclude is n minus alpha r. So for example, let's let n be 6, let's let alpha be 3, 2, 1, then, so we're permuting 1, 2, and 3 amongst themselves, 4 and 5 amongst themselves, and then the last letter has to be 6. So the generator set is S1 and S2, so we can permute these, and then S4, so we can permute the 4 and the 5. And the longest element of S alpha is, well, the most inversions we can put into this without sending letters outside of their block is 3, 2, 1, 5, 4, 6. Now, cosets of the form S alpha U are sets of permutations obtained from U by permuting the first alpha 1 letters and the next alpha 2 letters, etc. So U1 through U alpha 1 are going to stay in the first alpha 1 positions, and then U alpha 1 plus 1 through U alpha 2, sorry, alpha 1 plus alpha 2. Are going to stay in the next alpha 2 positions, etc. let's let S alpha empty set minus be the set of minimum length cosets, representatives of cosets S alpha U. Of the form S alpha U. So U is not fixed here. So S alpha empty set minus equals, now the minimum length representatives are going to be the ones where we've got all increasing letters here. So as few as possible, but we're not allowed to take letters from here and put them over there. So we'll have the increasing rearrangement of U1 through U alpha 1, followed by the increasing rearrangement of alpha 1, U alpha 1 plus 1 through U alpha 1 plus alpha 2, etc., such that U is any permutation we want. This is also, we can write this as the permutations, let's say V and Sn, such that SV is greater than V for all S in J. So if J is the set of generators, these are things that would increase in length for any generator that permutes letters here amongst themselves and then letters in these position amongst themselves. So for example, I'll put bars here just to separate the sections. So here's one minimum length coset representative. It's the identity element. Here's another one, 1, 4, 6, 2, 3, 5. And here's another one, 2, 4, 5, 3, 6, 1. So if we multiply on the left by any permutation in S alpha, or any generator in S alpha, we'll be increasing the length by creating more inversions in any one of these blocks. So we've always got increasing subsequences in each of the blocks defined by alpha. Now, cosets U S alpha, so I've got U on the other side now, are permutations obtained from U by permuting the letters themselves 1 through alpha 1. And alpha 1 plus 1 through alpha 2, alpha 1 plus alpha 2, etc., amongst themselves. So we get to permute these letters amongst themselves and these letters amongst themselves. Now let's let S empty set alpha minus be the minimum length representatives of these cosets. So these are, it's a little bit hard to write an expression that's analogous to this, but we can write an expression that's analogous to this. These are all the permutations in Sn such that Vs is greater than V for all generators S, and that's set J defined in terms of alpha. We can also say this is all the permutations V in Sn such that V inverse belongs to S alpha empty set minus, because inverting is just writing the generators backwards. And we can also say this is all the elements V in Sn such that 1 appears before 2, which appears before 3, which appears before alpha 1, and then alpha 1 plus 1 appears before alpha 1 plus 2, etc., which appears before alpha 1 plus alpha 2. So alpha 1 plus 1 before alpha 1 plus 2 before before alpha 1 plus alpha 2, etc. So for example, we have 1, 2, 3, 4, 5, 6, because 1 appears before 2, which appears before 3, 4 appears before 5, etc. I'm still using alpha equals 3, 2, 1. And then 1, 4, 5, 2, 6, 3. Maybe I shouldn't put bars here because, well, like it's okay in the identity. Now 1 appears before 2, which appears before 3, 4 appears before 5, and then 2, 4, 5, 6, 1, 4, 2, 3, 5. Again, 1 appears before 2, before 3, 4 appears before 5, and these actually are the inverses of the permutations I used in the last example. Now if you're wondering what the empty set is doing in both of these notations, if we have two compositions, alpha and beta, S alpha beta minus is the minimum length representatives of double cosets of the form S alpha U S beta, but we won't really need these. But that's why we need two different places up here. So empty set means that one of these is just not there. S empty set is the identity element. All right, now I claim that if we fix a composition alpha of n, then for all permutations W in the symmetric group, there is a unique factorization of W as W equals UV, with U in the parabolic subgroup S alpha and V in S alpha empty set minus. And also this factorization satisfies the length of W equals length of U plus length of V. All right, to prove this, let's write down a reduced expression. We can set V to, V is supposed to be the minimum one in the coset. So let's let V be the increasing arrangement of W1 through W alpha 1, W alpha 1 plus 1 through W alpha 1 plus alpha 2, etc. Then we'll let SI1 through SIL be a reduced expression for V. Now we'll use U and S alpha to permute these letters in each of the blocks. The letters are increasing in V until we get W. So permute the letters within each block to get W. Now note that the length of V, L, equals number of inversions in V or W that occur. Now, each block is strictly increasing. So all the inversions here are a letter in one block and then a letter in a later block. So the number of inversions in V or W involving pairs of letters from different blocks. All right, so I wanted to come up with a reduced expression for U. I'll just do that now. Let Sj1 through Sjp be a reduced expression for U. Then this number P is the number of inversions in U. And it's also the number of inversions in W involving pairs of letters in the same blocks. So pairs of letters sharing blocks. Now, since the total number of inversions in W is, well, either a pair of letters is in the same block or it's not. So the total number of inversions in W is the number of inversions of pairs which share a block plus the number of inversions involving pairs of numbers from different blocks. So we have that W equals UV with U and V in the right sets. And since inversions in W can be either between letters sharing a block or not sharing a block, the expression Sj1 through Sjp, Si1 through Sil is a reduced expression for W. That is, length of W equals length of U plus length of V. And as a corollary, we have that if we fix a composition alpha of n, then for all permutations W and Sn, there exists a unique factorization W equals UV with V in S alpha and U in S empty set alpha minus. And with the length of W being length of U plus length of V. We can get this from the other result just by taking inverses, and all the products of generators are just backwards. The end.